Okay, here we are, trig day number 7. We're going to get into inverse notation. All right, so if you have to memorize here, and we've talked about this a couple lessons back, but what I want you to be able to recall is your values of tangent. Here's your pi over 4, pi over 6, pi over 3. Okay, I want you to know that your tangent is equal to 1 at your pi over 4. Right? So over here in this quadrant, you'd have a -1. Down here, you'd have a +1, etc. -1 in the fourth quadrant. Okay, then you have your pi over 6's. That's where you'll have your 1 over root 3, which is equivalent to root 3 over 3. Okay, and that'll stay true through the other quadrants as well, just with a change in sign potentially. And then here we have a square root of 3. Don't forget that your tangent is 0 at 0, and your tangent is undefined at pi over 2 and 3 pi over 2. Okay, be proficient in your unit circle, cosine, sine, and tangent. Okay, so let's start talking inverse trig. First, let's talk regular trig, right? So the domain of any function, right? Sine here, the domain is going to be all real numbers, right? Because in here, I'm plugging in an angle of any measure. What I'm getting out is some ratio where that ratio is going to be between 1 and -1. Therefore, the range is from -1 to 1. Now, I'm about to flip that around, right? With inverse functions, the domain is going to be the ratio that I can place in there, where b, again, is still between 1 and -1. So that's going to be our domain. And our range is going to depend, right? Because this function, its inverse is not a function unless we restrict it. So let's see what happens here. So I'm going to flip the x's and the y's here by doing a reflection and a rotation. Now, this red portion will be red in a second here, is not a function unless I restrict it. So what we do is we restrict. In order to get a function, your calculator will restrict your graph from there to there. And that didn't hold to the true form of that. So there's a graph, not well sketched. Let me shift it a little bit, of arcsine. Okay, let's talk about its domain and its range. Well, its domain is -1 to +1, and its range is -pi over 2 to pi over 2. They could have taken any stem on this graph, because this graph will continue on forever, right? But they just took the closest stem. The calculator uses the closest stem to the origin. Okay, so our outputs for A, as you can see here, can be any values between -pi over 2 and pi over 2. Let's look at inverse cosine. Okay, inverse cosine, domain and range, all right? Inputs are angles. Those angles can be any value. Outputs from -1 to 1, just like we had with sine. Right? So the outputs are ratios, where b is between 1 and -1. Okay, angles inputted here. All right, when we flip it, what's going to happen, let's take this graph here. Let's duplicate it. Come on, duplicate. Oh, I didn't want that. Let's go back. Okay, so I've duplicated this graph. Let's go ahead and reflect it. Reflect it left and right, and then rotate. Okay, so I shouldn't have reflected it. I did this off camera, but here you can see that that this would be a nice inverse function, as it is, as we saw in the last one. It is a perfect reflection over the line y equals x, right? So you can see that. All right, so the cosine is restricted differently than the sine function for inverse. Okay, so what we do with the cosine function on this new one is we restrict it from here to here. Okay, that is inverse cosine. So inverse cosine, we're actually going to, again, we'll still have a domain from -1 to 1, but now the range goes from 0 to pi. Okay, so this point right here coordinates with this point down here. Okay, you can see the symmetry there and there. All right, so let's move on to arctangent. Again, though, this will be the angle it's inputted. And this will be the ratio that is outputted. Oh, I'm sorry, flip-flop. This is the ratio where b is between -1 and 1. And this is the angle wherewith arc cosine comes out to be between 0 and pi. Okay, so a little bit different than the arcsine. All right, arctangent. Arctangent's domain, we're going to restrict it here. We've got vertical asymptotes. So it's -pi/2 to pi/2, which looks familiar. We saw that with arcsine. Its range is all real numbers, right? There's no restriction on the upper and lower bounds of that function. So again, when we input an angle, we get out a ratio. When we input a ratio, we get out an angle. So these vertical asymptotes at -pi/2 and pi/2, they become horizontal asymptotes. And our graph of arctangent looks like this. So it just flips domain and range. So its domain now is going to be all real numbers, and its range will be between -pi/2 and pi/2. However, I should make those open brackets on the end, parentheses, because there are asymptotes and the value will only approach it but never reach it. So what does it mean? Right? What does this mean? What this means is find an angle x such that the cosine of that angle equals 2/3. Okay, so I don't know exactly what that angle would be. I'm not privy to that, but I do know this, that this angle x would yield me this triangle, right, where I'd have a square root of 5 right there. Okay, now if you see this notation with inverse cosine, that's assuming degrees. All right, so your angle would be given in degrees. In the next one, how are they different? Not a whole lot different. We'd still be yielding some angle x, but now it would be in radians. So this arc language here is radian language. Okay, so let's look at an example here. This right here is going to yield me, if you wanted to pause and just think about it, that'll yield me an angle. Right? And then this right here, well, that I don't even know what that is. Let's try again. There we go. This right here would yield me some ratio. So when I'm given this type of situation, right, I'm just going to draw a triangle. I'm going to draw an inverse tangent of 4/7 opposite over adjacent 4/7. And if I want to find the sine of that angle, let's call this angle theta. If I want to find the sine of that angle, I'm going to need the hypotenuse. Therefore, I got to use Pythagorean theorem. So it looks like 16 plus 49, that's 50. Oh gosh, is that 65? Let's see now, 50 and yep, and 15 is 65, so the square root of 65. So what would be now? Okay, I'm going to call this thing right here, I'm going to call this right here just some angle, and we're calling that angle theta. Right? We're calling that angle theta. So what would be the sine of theta there? The sine of theta would mean that x would be 4 over root 65. Or if you wanted to go varsity, 4 root 65 over 65. Both of those would be acceptable answers. Okay, let's take a look at this one here. All right, I'm taking the cosine of two angles. I'm going to call this one theta 1. I'm going to call this one theta 2. How do I know that these are angles? Well, because this says arc cosine, and so does that. Okay, so if I wanted to find the cosine of that, I'd just be finding the cosine of theta 1 plus theta 2. Now, I don't have a whole lot of information here. I don't have any ratios or anything like that. So, I mean, I guess I could do this. I could graph theta 1, and we could say that the cosine, the arc cosine of A, well, this is a ratio that we're placing in here. So if the cosine is A over 1, then this would be the square root of 1 minus A squared. And if this were the cosine of B, right, then I'd have B here, 1 here, and square root of 1 minus B squared. So if, again, this angle right here would be theta 2, this angle right here would be theta 1. So I would just construct using this. If I have the cosine of A plus B, calling this A and this B, I would have the cosine of theta 1 times the cosine of theta 2 minus the sine of theta 1 times the sine of theta 2. And I could just do a direct input of those values from here. So just that, for example, what would the sine of theta 1 be? The sine of theta 1 would be square root of 1 minus A squared over 1, right? So that's how I would find those, and I just directly input them. So let's see what I would do here. Let's call this theta 1. And sketch it over here. Theta 1 would be, let's see, cosine is 3/5. So I have a 3 and a 5. This is theta 1. That would have to be a 4. Okay, and then theta 2. Theta 2 would be cosine is 1/2. So that's 1, that's 2. That's got to be root 3. Okay, that's theta 2. All right, so then I just construct this. So it would be cosine. So if I wanted to do the cosine of theta 1 plus theta 2, I do the cosine of theta 1, which is 3/5, times the cosine of theta 2, which is 1/2, minus, right, because if I have A plus B, I do minus in between, the sine of theta 1, which is 4/5, times the sine of theta 2, which is root 3 over 2. Now, like I've said in the past, these will have common denominators. It looks like my answer here will be 3 minus 4 root 3 over 10. And I would be okay with that answer. That would be perfectly fine. All right, why don't you take a moment, although we're jumping into tangent. Why don't you take a moment and try 5B, okay? My hint to you would be to write this as a triangle. So draw it as a triangle and come back and just draw the triangle first and come back and check to see how I drew mine. Okay, so there's my triangle, right? It just yields me an angle. So if I want tangent of 2 theta, recall that tangent of 2 theta is 2 tan theta over 1 minus tan squared theta. Okay, so what do I need? I need to know tan theta. So over here, tan theta yields me, what is that, 3/4? So I'm going to plug in 3/4 here. So tangent of 2 theta equals 2 times 3/4 over 1 minus 3/4 squared. Let's do a little simplifying here. The numerator will be, what is that, 3/2. The denominator will be 1 minus 9/16. We do a little bit more work. That'd be 3/2 over, what would that be, 7/16. I'm going to multiply top and bottom by 16/7. Okay, that cancels everything in the denominator, and it looks like I get, it's 8, so 24/7. I think that's right. Let me make sure I didn't screw anything up. This would be 16/16 minus that. Yup, 7/16. Multiply top and bottom. And it looks good to me. So that would be tan 2 theta. That'd be your answer. All right. Why don't you try a couple of these? I'm gonna go ahead and do. I'm going to do 3 and 4. Okay, I'm going to go ahead and do 3 and 4. All right, so cosecant of arctangent of 3/2. So this is my angle, right? I want to do the cosecant of that angle. I'm going to figure out what that is, so I'm going to sketch. So the tangent of 3/2 tells me that theta would yield me a tangent of 3/2. So it'd be 4 and 9, which is square root 13. So the cosecant of this, remember cosecant of theta is the same as 1 over the sine of theta. So let's take the sine of theta and take its reciprocal. So what is the sine of theta? Sine of theta is 3 over root 13. So cosecant of theta would be root 13 over 3. Let's try another here. Sine of 2 arc cotangent of 4/3. So I'm going to call this theta. All right, so I want the sine of 2 theta, right? Recall that the sine of 2 theta is 2 sine of theta, cosine of theta. So first I got to sketch this scenario. I want a cotangent of 4/3. So that means I want a tangent. Oops, that means I want a tangent of 3/4. This is the same as arctan of 3/4. So if you don't like thinking in terms of cotangent, cosecant, secant, just flip them over. So the tangent is 3/4. That makes this 5. So this would be theta. So if I want sine of 2 theta, then I want 2 sine theta, cosine theta. So that would be 2 times the sine of theta times the cosine of theta, which looks like it would be 24/25. I believe that might be it for the day. Yeah, I think we're going to call that it for the day. All right, cool. So that's Trig day 7. Have a good